Hey guys, tonight we are going to take a look at a very interesting topic called accumulation functions. And I'm going to try to take a little different path this year for a variety of reasons, but we're going to really slow cook this and spread it over 2 days instead of just cramming it into one day. And I think today is going to give us a really solid, hopefully, a really solid understanding of how these functions work and do what they do. But quite frankly, an accumulation function is any function defined as an integral. Okay, so we could say that capital F of x is an accumulation function if it's defined as such. The integral from a to, we'll say, g of x of f of t dt. So a couple of characteristics here that make this an accumulation function. Number one, your lower bound is going to be a constant. Okay, it doesn't have to be zero. A lot of times it will be zero, but it just needs to be some kind of constant. It could be a 1, could be a -2, anything like that. Now your upper bound is going to be a function of x. Okay, and that's what really makes this an accumulation function. So now all of a sudden, instead of having this concrete constant as your upper bound, just like your lower bound, the upper bound is now a moving target. And that's the way I like to think of it. Your upper bound is a moving target. It's going to change on the fly. And so a lot of times it's going to be as simple as just x itself, but it could be x squared. It could be, anything that you could creatively think of in terms of x. Okay. Let's just say let's see if we can make up a fun little graph here. And we'll say this is a picture of lowercase f of t. Okay. So capital F is, in this case, let's just define it as the integral from 0 to x of f of t. So we'll go with the most standard bounds here possible. So think of it this way, and I think this is where the name accumulation comes from. You're accumulating area as you move from left to right. Okay, I think that's worth repeating and worth writing in our notebooks. We're accumulating area. Capital F as a function is accumulating area as you move from left to right. So in this sense, the starting line is at 0 in this particular case. And as x increases, we are starting to move across the region and we're accumulating chunks of area. So for instance, f of 1 is the integral from 0 to 1. Again, all the area bounded between the curve and the x-axis. Now, as we go to say f of 2, we're going to sweep a little bit further to the right and accumulate more area than we just had. So what's happening here is we're going to say that capital F is continuing to increase. And believe it or not, right where my pen is right now, capital F is still increasing. Okay. Now, for instance, let's zoom in on this point right here. Let's call this A, x equals A. All right, so at x equals A, lowercase f is decreasing. That's the graph we're actually looking at. But capital F is actually increasing because you're still accumulating a positive chunk of area because this little section right here is above the x-axis. So although it wasn't much positive area, you still accumulated a little bit. And he's going to continue, capital F is going to continue to increase right up until you hit that x-intercept, okay? That x-intercept is the first moment where we accumulated neither positive nor negative areas. And then moving forward, capital F is starting to accumulate negative little increments of area. So the cumulative total is starting to decrease right now. Okay, so the pink shaded section represents capital F increasing, and the green section represents capital F decreasing. And just to tie this in, we're basically going to take everything we did in our previous lesson, which was called the second fundamental theorem of calculus. We're going to tie it all together because it's going to make one monster topic. But if you recall, our second fundamental theorem of calculus says, again, if capital F is defined as the integral from a to g of x of f of t dt, then the derivative of that function is going to be f of g of x multiplied by the derivative of g of x. And so we'll keep that in our back pocket. And hopefully tomorrow we'll come back and we'll put everything all together. But for today, what I want to do is we're going to do a slow intro to these functions. And we're going to work our way through this worksheet. I'm going to do the first problem with you. And then I'm going to turn you loose and let you guys finish it. And I think you guys are going to slowly build confidence as the complexity of these problems grows. And again, so we're kind of exploring functions defined by integrals, which is another way of saying accumulation functions. And so we have our first accumulation function as defined right here. And then lowercase f, the function we're integrating, is over here. It's just this that solid linear function at y equals 3. So we're going to try to complete this chart. And the first thing we want to fill in is capital F of -2, which according to this definition right here is going to be the integral from 0 to -2, which we could rewrite as the negation of the integral from -2 to 0. Now, from -2 to 0, we're basically going to calculate this area right here of this rectangle. So it looks like it's got a base of 2 and a height of 3. So the area is 6. And of course, that region is above the x-axis, but we do have to negate it because we switched those bounds. So we're going to say capital F of -2 is equal to -6. Now, moving across that table, if we wanted to calculate f of -1, it would start off as the integral from 0 to -1, but then again, we'd switch the bounds and negate everything. And now the integral is measuring this little region right here. So that looks like we're getting -3. Probably my favorite integral of the whole worksheet here is going to be f of 0, or the integral from 0 to 0, which is automatically 0, no matter what lowercase f looks like, eh? And again, I think you could probably speed up the process, but I'm going to take my time and be somewhat methodical about this. F of 1 is the integral from 0 to 1, which means now we're measuring the area from 0 to 1. So we got ourselves, again, a very friendly rectangle. Everything's going to be rectangles here, so everything is super, super user-friendly here. F of 2 is the integral from 0 to 2, which is going to measure the area from here to here. Boom, 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 boom. And so we get a nice area of 6. Let's see. Running out of colors here. Let's try f of 3, which is going to be defined as the integral from 0 to 3. And so now we're extending our way up to here. So from 0 to 3, we've got a nice square now with an area of 9. And then I think, again, the 4, if we did f of 4, we're going to end up with a nice 12. Okay, so we could tell here, hopefully this table of values is going to help us answer some of these questions. On what interval is f increasing? And it looks like, assuming that we're working on the closed interval from -2 to 4, I'm going to say that f is increasing the entire time. So from -2 to 4. And in what intervals is f? Shucks. Hold the press. I got ahead of myself. All right, let me reread that first question, see if I can get this right. On what intervals is lowercase f positive? So the given function here, the very original graph, which was the line y equals 3, and that function is going to be positive. If we assume we're working in that closed interval, we could say from -2 to 4. Otherwise, it would just be from -infinity to positive infinity. The second question here, on what intervals is lowercase f negative? We would say none. Okay. And what intervals is capital F increasing? Okay. And it does look like capital F is increasing the entire time. At least you could say on the surface, our table suggests that for sure. But we've talked a lot about how these tables can be deceiving. But I think when you think about starting at -2 and working your way from left to right, we're just accumulating positive chunks of area the entire time. So our cumulative total is continuously growing. Okay, on what intervals is capital F decreasing? We'll say none. And now I think you can start to see the correlation between this first question and the third one. And again, the connection between the second question and the fourth one here. Okay, next, we want to try to come up with an algebraic rule for lowercase f, and that was just y equals 3. And could we come up with an algebraic rule for capital F? And again, that's just kind of studying the data in the table, and it looks like we could say something like y equals 3x. Looks like the output is 3 times greater than the input. Okay, so from here, I'm going to turn you guys loose and let you guys kind of walk through this investigative worksheet. And I think you're going to really build some solid, deep understanding. What we're seeing here in example number 2 is it looks like to me the lower bound has changed on the definition of capital F, which was kind of a nice little twist. And it looks like they lowered the function. Looks like lowercase f is at y equals -2, and we can see how that impacts the way that we accumulate area as we move from left to right. Scrolling down here, the third one, it looks like lowercase f is now a linear function that has a slope of 2. It's somewhat, sometimes below the x-axis, sometimes above. So that's going to stretch our knowledge, our understanding. Number 4 is now a decreasing linear function. And the last one, number 5, is going to have all sorts of fun waiting for you. And at times, this is going to feel very tedious filling in the tables, but I think this is where the real work gets done when we kind of open up the hood of the car and start to figure out how this car really operates and does what it does. Okay, now what I want you to do, if you'll notice as we move on here, we do have all the answers and some nice commentary here. So as we get stuck, if we need to kind of look at the answers and work backwards, we can do that. And one thing I want to point out is, when you sketch number 4 here and you come up with your sketch for capital F on number 5, really work hard on those sketches. And I want you to really focus on how you draw the concavity of capital F and how something like that connects with the given picture of lowercase f. So hope we do well tonight. Good luck. Of course, if we do hit some roadblocks, ask as many good questions as you can, and we'll take it from there. All right, have a good one, guys.